Hello everyone. In this video we will continue to examine topic 2.1 motion, and in particular we will continue to examine the equations of motion for uniform acceleration. A careful observer in noticing or in watching our previous video would have noticed that we derived 3 equations here, and there are actually 4 total SUVAT equations. That's because these first 3 can be acquired by straightforwardly considering the graphical techniques and graphical analyses for a constant acceleration that we have already considered. Unfortunately, the fourth, in order to get the fourth, you need to do a little bit of algebra, straight algebra, using a couple of the other equations. So the derivation of the fourth can be done a number of different ways. I'm going to show you one of them, which involves combining a couple of these equations. Notice that in equation 1, our missing variable is the displacement. In equation 2, our missing variable is the acceleration. In equation 3, the missing variable is the final velocity. And so for our fourth and final equation, it can be very helpful to have an equation sometimes that actually does not involve time. And you'll notice that each of these 3 equations involve time. That's part of why they are easily derived from a velocity time graph. And so what we're going to do is we're going to combine 2 of them to eliminate the variable t. So start out with equation 3, that is s equals ut plus 1/2 at squared, and equation 1. And we're going to rearrange equation 1 to solve for the time, where they're going to take that value and plug it in for the time in equation 3, and then do some algebra and make it a little easier to read. From equation 1, we know that t is equal to v minus u divided by a. And so we take this expression and we plug it in for t in equation 3. This gives us a pretty ugly equation here, but with a little clever algebra, we can actually simplify this fairly straightforwardly. So once we insert this variable for t, or this expression for t into our equation, we get the displacement is equal to the initial velocity times the change in the velocity over the acceleration plus 1/2 a times the change in the velocity over the acceleration squared, okay? And we're going to multiply both sides by 2 times the acceleration. The reason for this is not obvious yet, but will become apparent in a moment. So take for granted that I can multiply both sides by 2 times the acceleration. That gives me 2as on the left-hand side. And then what happens on the right-hand side? Well, take a look at this expression. This becomes u times v minus u divided by a, okay, times 2a. Our a's cancel in this particular term, and that gives us 2 times vu minus 2u squared, okay, u times u. And then in our second half of the equation, we can see that by multiplying by 2a, we just directly cancel out this particular term, that 1/2 a term right there. And then we can expand v minus u squared. Remember that v minus u squared is not the same thing as v squared minus u squared. Your algebra teacher would have a fit. You need to distribute terms, use FOIL or whatever technique you've been taught, and remember that that middle term, minus 2 times v times u, is very important. Then you spread this all out and you realize, okay, I have quantities that cancel here. In particular, if I have a 2vu here term over here and a minus 2vu term over here, then those two cancel. What I'm left with is v squared plus u squared minus 2u squared, otherwise known as v squared minus u squared. And that gives us our fourth and final equation, which says that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. This is almost always the trickiest equation to use. Sometimes in solving it, you end up needing to take a square root. It is also very common that students will forget the sign on either the acceleration or the displacement. Remember, both of those are vectors. So just watch out as you move forward. Following this particular derivation, there are a number of examples, okay? And you should get very familiar with these examples of using those SUVAT equations to find missing quantities. You're going to use these throughout the course. You should be aware that they are available in the data booklet itself, but hopefully by the end of this unit, you actually have them memorized. It would not surprise me, and actually I would expect it if you have done sufficient practice. So